The following presentation will be based on Dijkstra's algorithm, a final project for a computer science course, specifically design and analysis of algorithms. My name is Kalade Bamadeli, and my consulting group members are Austin Yule and Shaheen Rahimani. Our objective is to use Dijkstra's algorithm to find the shortest path between two specific vertices in a weighted but undirected graph. First, I would like to briefly explain Dijkstra's algorithm. This algorithm finds the shortest distance between nodes or vertices in a graph. We choose a starting vertex, then we find the distance to all the other vertices. We maintain two lists, one of which is a list of visited nodes, while the other list consists of unvisited nodes. The result will be a shortest path tree. Our real-world problem approach to applying this algorithm was to represent a city's map as an undirected graph with the streets representing edges of a graph and the intersections representing vertices. We provide a starting point and an ending point in latitude and longitude format. Then we use those points to find the nearest vertices to those points in the graph. We then apply Dijkstra's algorithm to find the shortest path between the two specified vertices. We mainly used three data structures to accomplish this task. We used an adjacency list to represent the graph, a hash map to store the vertex arrays consisting of a list of nodes, and a stack for storing the vertices as we find the shortest path. Our data set was populated using Bridges. Bridges is a data distribution platform that provides reference libraries. It allows data providers to manage data access using APIs. We use the OpenStreetMap API, which consists of real-world data concerning city streets, intersections, and distances between them. I will now show you our code and do a brief demonstration. We wrote this program using Java. We have three classes. Our first class is our graph class, which is the constructor class for the hash map and for the nodes. The second class is our data test class. Here we created the adjacency list representation of a graph using OpenStreetMap data for the city of Savannah, Georgia. Third is our main class, which is where we get input from the user to determine the starting point, ending point, locate the nearest vertices to those points, implement Dijkstra's algorithm, and find the distance from starting point to all other vertices, then find the shortest path between starting and ending vertex. I will now do a brief demonstration. Immediately upon compiling, we see the number of vertices and edges for Savannah, Georgia in total. We are now prompt to enter the starting latitude in degree format. We are now prompt to enter the longitude. Now we are displayed the starting point, the vertex closest to the starting point, latitude and longitude, and also we display the index number for that vertex. Now we are prompted to enter the destination latitude. And now the destination longitude. Our result is the minimum distance displayed in meters, which is 596 meters, along with this path, which is displayed in a format of latitude and longitude and the index number for the vertices. We now have a shortest path from our starting point to our ending point. In conclusion, we were able to successfully implement Dijkstra's algorithm to find the shortest path between any two vertices in our map graph. This solution is always optimal because it does not rely on any previously known routes or information. The minimum path will always be relative to the input data. It uses the greedy algorithm, which means it makes the locally optimal choice at each stage. This is basically the concept of GPS navigation. You enter a start and the ending point, and the GPS tries to find the shortest route between both 2 points. Upon completing this project, my teammates and I will now reach out to Google and tell them that we have mastered Dijkstra's algorithm and we are ready to take over the Google Maps department. Thank you and wish us luck.